lecture of 2021. And what a finale. The finale will be with Aditya, Dr. Aditya Joshi, who did his PhD from Sheffield with me, working mainly on the very hard problem of sarcasm detection. We indeed have very pioneering papers, I would say, in this area, very hard problem. And Aditya's work appears in top conferences. His work also has been cited by MIT Technology Review and CACM Technology Review, which always keep track of very cutting edge, substantial progress in science and technology. Right now, Aditya is in Australia working for an industry. Before that, he did his postdoctoral with the equivalent of National Science Foundation, CSIRO, in Australia. And Australian government has been so impressed with Aditya that they have offered him permanent residency, and he can be in either country, both in Australia and India. This kind of privilege is reserved for only extremely qualified people with a lot of accomplishment. But Aditya has to go far. As a teacher and guide, I must remind him that you have to keep walking, okay, and reach newer and newer heights. Aditya is also an excellent teacher. So over to you, Aditya.
Thank you. Thank you, sir. My name is Aditya, and my name is Aditya Joshi, and I have misspelled my name here. Sorry about that. But I am a student of Professor Pushpak Bhattacharya, and I use simple present tense for a very specific reason. I first became a master's student under him. I did my MTP in sentiment analysis, then my PhD in sarcasm detection. And of course, he has been my life mentor, and I reach out to him for important professional and personal decisions. Anyway, so I'm really happy to be here. And today I'm going to share a talk with all of you. You are aware of the title of the talk, but before I begin, I would probably remind you that this is an industry talk. So I currently work at Seek. Seek is an employment marketplace, and it operates in around 15 countries. We reach out to more than 200 million candidates and 1 million hirers. Essentially, it is a job website which matches candidates and hirers. So as you can imagine, there's a lot of potential for AI and NLP in a field like this. This talk that I'm about to present was shared with designers, engineers, data scientists, and project managers in the team. So it is essentially a mix of intuition and coding or application. So I hope you can see my screen. But before we begin, can I just request all of you to please in chat, can you just and on a scale of 1 to 5, can you just put a number in chat where you tell me how familiar are you with transformers and BERT, 5 being highest. Thank you. Awesome, really fast responses. I noticed Sandeep Matthias's response. Sandeep Matthias is a friend, of course. So thank you very much. And let's begin with the presentation. I am sharing my screen, and I'll first start with a PowerPoint presentation, a few slides, and then I'll move to a Miro board. So I hope you're able to see my slides. So I'll start the discussion of language models, and especially transformer-based language models, in the context of ExcelNet, which is one of the transformer-based language models. But this particular paper actually looks back at transformer-based models in a very interesting manner. So how did I first study language models? The year was 2009, and I studied language model as a mechanism of estimating the probability of a word sequence. So if you have a word sequence of W1, W2 up to Wn, you apply chain rule and you assume that a word depends only on the word before it. Well, in this, and as a result of which, you decompose this distribution, this probability, into probability of W1, probability of W2 given W1, and so on. We know this as a bigram assumption. And there are other nuances in language modeling, like the independence assumptions and smoothing, which we're not going to get into the details of. However, what we see here as language modeling, where a word depends on words before it, came to be known as autoregressive language modeling. And I would like to start this talk by really comparing these two paradigms of language modeling called autoregressive and autoencoding. And in fact, the idea of getting me to share my thoughts came about after Professor Pushpak and I were discussing autoencoding and autoregressive language models a few days ago. So what is language modeling? The goal of language modeling is to estimate the probability of a text sequence, which could be x1, x2, up to x10, where x is the word. Let's compare autoregressive language modeling with autoencoding language modeling. And I'm going to use this very familiar paradigm of distinguish between, the way we used to study it in school, right? So if we had to distinguish between autoregressive language modeling and autoencoding language modeling, what would it be? An example of autoregressive language modeling is n-gram language modeling, where the fundamental idea is estimate the likelihood of the nth word given a context of a sequence of n-1 words. In contrast, autoencoding language modeling, as seen in the case of BERT, deals with estimation of the likelihood of k masked words in a sequence of length n, given a context of n-k words. So if you had a sentence of n words and you randomly masked k words from the sentence, and you learned a model which learns to predict the likely words that were at the masked position, you would be doing what is called as auto-encoding language modeling. And if we had to really look at the equations of the two paradigms, we see that autoregressive language modeling here maximizes, essentially estimates the parameters theta, which maximizes the log probability, where essentially there's a conditional here based on the word at position t and all the words before it. And this is how it gets decomposed. In contrast, auto-encoding language modeling has a similar conditional probability, but now it is concerned with predicting the masked words given the words which are actually available. As you can see, the density estimation in autoregressive language modeling is explicit, which means that you can really count the number of times these words appear in a certain sequence, as a result of which you can estimate the probability. In contrast, autoencoding language modeling deals with reconstructing the original data. And in fact, autoencoding really comes in from speech processing, where the idea is to learn autoencoders which generate the same input from itself. And the goal is essentially to learn the model. As a result, some pros and cons of autoregressive and autoencoding language modeling are understood. So autoregressive language modeling does not introduce additional noise, whereas autoencoding language modeling introduces these masked tokens in the form of special tokens called mask, as a result of which it causes noise, it introduces noise, because you may actually learn things which are not likely at that particular position, and you are introducing mask labels, which means that you're losing out on the information that was available in the data. Autoregressive language modeling, in contrast, models unidirectional context, and it assumes that a word depends on words before it. That is indeed how we utter language or speak language, but meaning of a word can be derived from the words around it, which is essentially the idea that BERT tries to use when it models bi-directional context. I'm going to stop here with this particular presentation, and I'm now going to move on to the other presentation. Sorry, was I sharing my screen at all?
Yes, yes.
Oh yeah, okay, sorry.
Yes, it was sure.
Sorry, I just got confused. Like maybe I was not. Okay. So now, sorry, can someone confirm if you can see a browser miro.com?
Yes.
Oh, great. All right. So now we start our discussion focused on BERT. And like I said, the idea of this presentation is to give the intuition and in some way discuss my understanding of BERT via a very linguistic or philosophical perspective. You will see parts of code in this presentation. So what is BERT? BERT stands for bidirectional encoder representations from transformers. It's quite a mouthful, but we will slowly dissect what this long form of the word means in the hope to understand it better. So what is BERT? BERT is a language model. That is, it represents a text as a dense vector. And it is not just any dense vector, but we hope that this dense vector captures its meaning. This is a fuzzy idea which we are going to discuss further, but for now, let's focus on the word text. Text, in essence, is a string. So it could mean word, phrase, sentence, document. So we are using the word text rather loosely here, although BERT is trained on a very specific kind of data sets. But why do we want to train a language model which represents text as a dense vector? Because eventually we want to learn predictive, we want to have predictive classifiers or models on the top of these vector representations. So they could be they could be models which give you similarity, they could be models which classify, and so on. You can imagine that since we are a job matching website, where I work for a matching website where we match candidates and candidates resumes with the job descriptions, you can imagine how the two how similarity and classification are really important tasks for us. But then what does capturing meaning mean? What does capturing meaning really mean? And therefore I would like to play a small game with all of you. So let's look at this first sentence, and I would like you to suggest words that fill the blank, right? So if the sentence is, I got my second dash last month, what would it be? And there are no wrong answers. Sorry, I can't see the chat if someone's typing. Can someone say it aloud?
Offer,
Yeah.
call,
Okay,
hike.
great. I got my second offer last month. I got my second call last month. That's great. That's great. Swaroop, what do you think? Sorry, Swaroop, you are the only person I have interacted with in the past.
It can be anything.
Can you
So,
think of a word? I got second dash last month.
so the job offer.
Okay, great. All right. So job offer seems to be the phrase that all of you prefer. And of
No,
course,
Aditya, there is also an interesting word, hike. I got my second hike.
exactly. Yes.
I mean,
I
some
got,
Sandeep Singham Setti has written this.
oh, nice. Yes, absolutely. I got my second hike last month. Exactly.
And Tejpal has written, I got my second promotion. Interesting.
Very nice. Yes, exactly. But we see that all of us are really operating in a certain zone. And I think that these answers are coming up primarily because I described the company I work for. And that is my hypothesis only. But when I did this talk in my company, in my office, it was around the time everyone was getting vaccinated in Australia. And so I got my second dash last month. Actually, overwhelmingly got the answer. I got my second vaccine last month, or I got my second dose of the vaccine last month. And therefore, the idea really is that when we try to understand the meaning of a particular text, we actually naturally learn to fill in the blanks based on what we understand about the particular piece of text and what we imagine the particular piece of text means. All the words that you all of you mentioned are correct. And in fact, when you say I got my second hike last month, I got my second promotion last month, I got my second job offer last month, we can all see why this person is actually making that suggestion. You are actually associating the word got with something that you get. And in the context of what I described Seek does, you probably suggested something around employment and a professional advancement. And that really is the basic idea that I want to drive home, that when we understand language or when we understand meaning, this is really what we understand. We understand how the words associate with each other. Let's look at the second example now. Which pair below seems more likely to be taken from a book? So the first one is, I went to school, the elephant nodded. And I went to school, the teacher welcomed me. So any answers? So I mean, essentially, which two sentences are likely to be next to each other in a book? So I imagine that most of you are thinking that I went to school, the teacher welcomed me is more likely to be really taken as it is from the book, because these two sentences are very absurd. They're not related to each other. And these fundamental ideas of understanding meaning are also BERT's training objectives. They are masked word prediction, which means try to predict missing words at a given position. Specifically, learn a model which maximizes the likelihood of words which have been masked. And next sentence prediction, which essentially is an output label that indicates whether two words are next to each other or not. Several variants of BERT have been introduced and discussed. Some of them are Roberta, DistilBERT, which is a so-called lightweight kind of BERT. You can also optimize BERT for certain domains. So BERT for biomedical documents is called BioBERT. BERT, a library for BERT which is useful for getting representations for sentences, is called SBERT or SentenceBERT. And ExcelNet is essentially BERT with some sort of auto regression involved. And in fact, it is also called as permutation language modeling, which is a rather crazy idea according to me, but it's very interesting. Now, this slide is, I think, the reason Pushpak sir asked me to give this talk. I honestly believe that this is some discussion that we had a few days ago, and this idea of BERT is a vacuum cleaner is, I think, an idea that helps me understand BERT. BERT is a vacuum cleaner. Why is BERT a vacuum cleaner? Let's look at the vacuum cleaner on the left. The basic component of a vacuum cleaner is ability to clean. There are many ways to clean your floor. You can use a broom and wipe it, or you can use a suction to suck the air, or you can do other things. So essentially, a vacuum cleaner need not necessarily only use suction. But as a device to clean, as a mechanism to clean, it adopts the strategy of using suction. And once you have this vacuum cleaner, which is the base unit, it remains the same. Its basic function is ability to clean, and it does it via suction. And we understand that there are many ways to clean, right? You can use a broom and wipe it and so on. But once you have this vacuum cleaner in place, you can attach different things to the vacuum cleaner, depending on what surface you want to clean. Right? So you can attach a different head to the vacuum cleaner to clean a carpet, to clean tiles, to clean ceiling, to clean car seat. I won't get into details of how each of them are different. I hope you get what I'm trying to say. In contrast, BERT is also doing the same thing. There are many ways to learn language, or there are many ways to interpret what it means by a model learning language. Just the way a vacuum cleaner adopts the strategy of suction, BERT adopts the strategy of predicting missing words and sentence relationships. This is not the only way to for a model to learn language, but this is the strategy which BERT adopts. And once it has these unsupervised large corpora, it learns language via missing words and sentence relationships. And just like vacuum cleaner, you can use BERT by attaching different heads. And that is really the idea of fine-tuning a classifier, where essentially the main model has learned from a large data for no specific task, but you can adapt the model for specific tasks like sentiment analysis, like named entity type recognition, NLI, etc., natural language inference, etc. And so I'm going to now talk about the history of BERT in the form of a comic book. So the year was 2017, And there was this model called the transformer, which was introduced. What did transformer do? Transformer had an input sentence and an output sentence. And transformer was this black box that you see here, and it could be used for machine translation and question answering. Let's look at a very high overview of what the transformer was like. So essentially, if you have the input sentence, she eats pizza, the output sentence would be lei mangia la pizza in Italian. And the transformer is essentially learning to generate the output sentence via the input sentence. Since both of them are sequences, this is actually called a seek-to-seek model, or a sequence-to-sequence model. And therefore, let's look at what transformer looks like one level deeper. It has a set of encoders and a set of decoders, which look like this. And if you drill down further, what these encoders are is essentially a repeated sequence of encoders and a repeated sequence of decoders, right? This is often referred to as a stack of encoders. We notice that the encoders are going up, the arrows are going up. And once you reach the highest level of encoder, this final state, learned state from the encoder becomes an input to the decoder, as you see in these arrows, where the decoders are also arranged in a stack or a sequence. They are one on the top of the other. And if we had to get into the details of what encoder and decoder are, then these are the repeating blocks of encoder and decoder. Encoder uses self-attention followed by feed-forward, and decoder contains two components: self-attention for the sentence within itself, and it also takes as input representation from the encoder and applies what is called as encoder-decoder attention. And this is how encoder and decoder are intuitively different in their structure. But I'm going to go a level deeper into what I understand the philosophy behind self-attention and encoder-decoder attention in transformers. And I have this here. So what is attention? Attention is a vector indicating relative weights between features, which are words in this case, which are learned as a part of a neural network. As a result, these weights capture what contextualized semantic relationships among features, as a result of which they're often called as semantic embeddings. So how do I compare the two types of attention? Self-attention and encoder-decoder attention, which may be called as cross-attention. The philosophical intuition, which is intuition from our real life, is to learn from your experiences, you have to look within and introspect. So if we succeed at something or if we fail at something, we need to look back and understand why we did not do well. And this idea, I think, maps to the idea of self-attention, because it tells you how a word in a sentence is related or close to other words in the sentence. So for example, in the sentence, she eats pizza, for eats, pizza is more important than she, as seen in these graphs here. And why is pizza more important than she for eats? Because pizza is an edible entity, and the verb eats is closely related to pizza as opposed to the pronoun she. Encoder-decoder attention, in contrast, follows the philosophical intuition of learning from others. How do we learn from somebody else's experiences? When we read biographies of a person who inspires us, we are often in awe of how they handled certain situations in their lives and difficulties in their lives. And in some way, we map their lessons to our situation. And we often learn from others by being able to establish this relationship. And this idea is, according to me, captured in the form of encoder-decoder attention, where for a word, you are learning weights in the output sentence, relative importance weights. And therefore, for the word eats, mangia in the output sentence, which is the translation of eats in Italian, is more important than lei, which means she, and la or even pizza. So lei means she, mangia means eats, la is the, and pizza is pizza. And so as you can see, for the English word eats, the Italian translation has the highest attention, and the second highest is pizza, which is a related word related to eats. How is attention really implemented? Attention is really implemented in the form of query and key value pairs, which is an idea which comes from information retrieval. And the reason I have this slide is because when I first made this presentation, majority of the audience was from an IR background. So the idea really is that if you have a word, you're first trying to see what are the important neighboring words with respect to the current word, and how important are these neighboring words themselves. So let's look at this diagram, which I have lifted from a blog. So let's imagine that we're trying to get the reweighting for the word Michael. In the sentence, Anthony Hopkins admired Michael Bay as a great director. You notice that Michael has the highest weight with itself, but because Michael is also a name of a director, the word director may also have a high score. And the idea being conveyed here is exactly what I tried to convey with eats and pizza. Corresponding to eats, pizza has a higher weight in comparison with other words in the sentence. And how important are these words in itself? They get multiplied to get the resultant reweighted vector. And therefore, if you had to really break down this formula, which often is brought up in the context of multiplicative attention specifically, I interpret it as this: how is this word related to other words that are also important for the meaning of the sentence? So this word borrows some meaning from the other words that it is close to. And if those words are also important, it needs to take a share of their meaning. So with this basic background in transformer, let's go back to our story. So transformers were used for machine translation, where this scientist thought, how can I use this brilliant innovation to learn a language model? Because transformers, in a sense, were for translation or sequence to sequence generation. As a result, the person looked down under the hood of the transformer and said that there was an input sentence, a stack of encoders, as we saw, which are converted to a vector representing the sentence, and decoder, which generates the output sentence one word at a time. Transformer maximizes the likelihood of the true output sentence for a given input sentence, which essentially is the formulation used for something like machine translation, which is one of the tasks transformer was first introduced for. So the scientist is thinking, I like the vector. The vector seems useful. It is capturing meaning. So can I remove the decoder and instead learn the vector for some particular task? Because essentially, if we are trying to learn the vector, it has to be for some learning task. And therefore, the scientist has to think for a learning task for this vector. As a result, the scientist starts thinking, what can the task of meaning be? What does it mean by meaning? What does it mean by meaning of language? And I'll bring you back to the idea that the ability to clean could have been done in many ways, but the vacuum cleaner adopts a certain strategy. Similarly, in BERT, this intelligent scientist adopted two dummy learning tasks. The scientist said that I have a large data set of Wikipedia documents, medical documents, or job ads in our case. You can actually cook up two tasks: a masked language model or a masked word prediction, and next sentence prediction. And I could optimize the transformer, the encoder of the transformer, on these particular tasks. So for example, if you have a document that looks like W1, W2, W3 dot, indicating it is the first sentence, W1, W4, W5 dot, indicating it is a second sentence, and so on. So essentially, you can start with a large unlabeled corpus. So it is not trained on any task. You're just downloading large dumps of data. This scientist randomly masked words. What does it mean? The scientist picked the first sentence and randomly put a blank instead of the second word. Similarly, the scientist also picked the third sentence and randomly put two masks at the two positions. So this is randomly done, which means that it is not predictable. You generate multiple versions. And the model is learned so that it applies the stack of encoders and it tries to predict W2, W2, and W9 because these were indeed the words present at these positions in the original document. And it also will try to predict false because these sentences were not next to each other in the original document. So the model is being learned on two tasks, masked word prediction and next sentence prediction. And this trained model can actually be used to learn representations of sentences. We note that this model has not been trained on a labeled data set and it has not been trained to solve any specific NLP task as such. It is just the base of the vacuum cleaner, the one that has learned to clean. As a result, when BERT came about, this new word became popular, which is pre-training. Pre-training is like preparing for an exam. It is pre-training, training before training. So pre-training corresponds to training on unlabeled data just to learn vectors that capture meaning. And therefore, let's revisit the name. What does this mean? Now, does this name make more sense to us? BERT is learned from transformers because it uses the encoder of the transformers. And it actually learns representations from transformers because that is what it learns to do. It learns to represent text as a vector. And it is a bidirectional encoder. So it takes the encoder from transformers and uses it for representations. And that is how I understand the name of BERT, which is a long name in itself. And if we had to look for a diagram from the original paper, because I've used some colorful graphs here, colorful images here, this is the diagram from the paper, where essentially you have an unlabeled sentence A and B pair. You create a masked version of the sentence and a masked version of the second sentence. You pass it on to the BERT model, and it learns to predict these two labels: NSP, which is next sentence prediction, and masked language model, which is predicting the masked word. And how can we use BERT? If you have no training data set, you can actually, so now this is where the very coding oriented part of the presentation starts. So there's a lot of code which you'll see. So when you have no training data set, you can essentially use a pre-trained BERT model and pass a sentence and get a vector, right? So this is a Python code which shows that you first imported the sentence transformer library. You loaded a model called paraphrase distill Roberta base 1, which is a kind of model. There are different ways you can initialize this model depending on what kind of model you want. You pass the sentences in the form of a list and you call model.encode, which gives you the embeddings. So essentially, this is really the embedding printing part of the code. Which means that if you do not have any training data set, you can still use BERT in some way. You can actually use this vector as a feature vector for a statistical classifier as well. Or you can use this to measure similarity of sentences, and it does pretty well. What happens when you have an unlabeled training data set? So you could be working on a very domain-specific problem. You could be working on sentiment analysis for travel reviews, for example. How would you do it, right? So you could use an unlabeled data set, unlabeled training data set, by essentially using a BERT pre-trained model and fine-tuning it for your domain. So the examples that I've given is BioBERT and something else. So from transformers, you essentially import Roberta tokenizer and the Roberta for masked LM, and you import the trainer, which allows you to fine tune it. So the tokenizer splits the words into tokens, and the model essentially you're loading a pre-trained model called Roberta base, and you are fine tuning it for your data set, where you have loaded your data set in this particular variable called data set. So essentially, you can leverage on the large corpus that Roberta or BERT was trained on, and you can fine tune it for your own domain, for your own problem, for your own data set. And finally, the third case is the most useful and the most, and it actually connects us back to the whole vacuum cleaner example. You have the base vacuum cleaner, you attach different things to get it to do different tasks, to clean different surfaces. And therefore, when you have a labeled training set, what you can essentially do is you can use the word pre-trained model, get the vector, initialize the vectors, and you perform some task-specific training based on the label. And that is where you get the model, which could be something like sentiment classification, which could be our paper on job candidate similarity scoring. So it's a paper which says, given a CV of a candidate and given a job description, how similar are they? Can we actually use BERT representations for that? And therefore, adapting the diagram which we saw, and this is a diagram from the original BERT paper adapted, you see that here, the words here, the output label for sentence pair classification uses the representation of C, the first token, CLS token, to get the class label. So this is fine-tuned on the sentence pair classification task, which captures relationships between two sentences. So this could be MNLI, which is NLI, which is natural language inference. So does one sentence entail the other, for example? The second kind of task that you can use BERT is single sentence classification, which is SST, which is the sentiment analysis dataset, and COLA, which is the linguistic ability dataset. So it predicts the difficulty level. So essentially, you can fine-tune the BERT representations for a particular sentence, and you notice that in this case, you provided only one input, and in this case, there were two inputs because this was a sentence pair classification task. Finally, you can also use BERT for question answering task and single sentence tagging task, which is named entity recognition and question answering respectively. So you can supply the question and a paragraph, and BERT gives you the phrase within the paragraph which answers the question. So for example, if you have a question, if you have a paragraph saying what an exciting city Delhi is with its 50 million people and great sights and sounds. This was an example which Pushpak sir gave 2 days ago. And if your question is what is the population of Delhi, you want the classifier to learn the exact phrase, which is the population number in the particular sentence, the paragraph. And what does the code here look like? The basic fundamental code really looks like this, where you use a model. You load a pre-trained tokenizer and a pre-trained model using transformers. And finally, you load your labeled data set in train and validation, and you essentially train the model using the trainer. And once you have saved the model to a file, you can use BERT for sequence classification again to make the prediction. So these are really fundamental pieces of code to get people started with using BERT as classifiers. So that is all from me. I would really like to leave all of you with this basic idea that BERT is a vacuum cleaner where the fundamental ability to learn language has been dumbed down or approximated to these two tasks. And you can essentially use BERT for a variety of tasks by placing these heads on the top of the BERT model. So yes, that's it from me. Thank you.
Thank you, Aditya. Now, let's have question answer discussions. I see a comment from Swaroop on the chat box. A peculiarity here, your psychological mindset also drives the decision. Is that a characteristic in language models too? Maybe their own bias.
Yeah, that's true. But when we are training large language models where we see those phrases very often, we hope that the bias is not there, right? But it has been understood. And in fact, there are lots of papers in NLP conferences in recent years which talk about uncovering biases in language model, right? So if you use the word nurse, is there a certain gender that comes to your mind when you train a language model? Or if you use a language model for predicting Dash is a nurse, does it predict he or she, for example? Similarly, Dash is a doctor, does it predict one gender or the other? So these biases do creep in terms of occurrences. And there is explicit work in language model which works on debiasing these models. In fact, you may have noticed that you may have heard of a case from Amazon where they were using a recruiting software, and this is in the news. and it was found to have some biases in shortlisting because it preferred certain candidates over others, candidates of certain backgrounds, and they had to retract the model. So Swaroop, what is a pretty cool platform for presentations?
That Miro.com.
Oh yeah, it's a free website, and you can try it. It's quite cool, and it allows you to zoom in, zoom out, and it's a lot like Paintbrush, but Paintbrush allows you to zoom in and zoom out.
Yeah.
Thank you. Yeah, the word
There is-
autoregressive. So can you, Ankush asks, can you tell more about autoregressive term? So the word, so I was just discussing this with Pushpak sir 2 days ago, and I'm going to borrow from that discussion itself, because that was the time I paid a lot of attention to that word. And I don't mean attention in the transformer sense. But autoregressive, so autoregressive comes from time series monitoring. So you see autoregressive time series monitoring techniques, which essentially say that we'll predict something for today based on something that we know in the past. So let's assume we'll predict the stock price of this company today based on the stock prices of the company in the last 7 days. So regression is essentially learning to predict real values, right? The way we understand regression, classification and regression. But auto regression is essentially learning from itself. So you learn the curve of the line and you predict the next term in the sequence, the next unit in the sequence. That's the base. That's where the word autoregressive really comes from, in my opinion. Given the same performance, which model needs a lower size, transformers or LSTMs? The point of the question is, as we build more sophisticated model, do we decrease the size necessary for the same performance? Which model needs a lower size? Do you mean dataset size, or do you mean size as in the
Number
amount?
of neurons.
Sorry,
The number of neurons or the layers necessary.
In my experience, transformers generally perform better than LSTMs, right? Because they capture multi-headed attention. And I mean, by transformers, I'm assuming that you mean BERT representations for classifiers, right? LSTMs have a linear structure, and therefore they rely on a linear kind of a model. Right?
Okay.
Hello, am I audible?
Yeah, you're audible. Sorry.
One thing I want to ask, like, BERT is a mass language model. So for mass language, we are having the blanks, and then we are filling those blanks. So that is also done based on the pre-trained model, which I think is similar to autoregressive. Like, that is also a time series model, as you said. So it is also done based on the previous data set. So I have a doubt here, like, what is the major difference between both?
Sure. So that's a good question. So actually, the terms auto-regressive and auto-encoding to refer to LSTM and BERT in such a way appear first in the ExcelNet paper. And BERT uses context from both direction, as a result of which it is referred to as auto-encoding and not auto-regressive. So the difference really is BERT uses information from both directions.
Okay.
So Swaroop, related to your thank you. Swaroop, related to your question, how important is pre-processing in language modeling? What if somewhere there are some incorrect spelling words or an ill-formed sentence? So in fact, which is also why you observe that a lot of these transformer-based language models have a strong component of tokenizer. They actually use they actually use piecewise word embeddings, piecewise token embedding. So they split a word into its components, as a result of which they try to factor in the shared representation of different form of words. What do I mean by that? The word reconsideration and the word considering are different. They have different pos tags, but there is a commonality in meaning. So I think a lot of these transformer based models do these piecewise representations to get around the problem of and therefore pre-processing is absolutely important, and that's how they establish correspondence between different forms of a word. And what if somewhere there are incorrect spelling words? Yes, I mean it will introduce errors in the model, right? So I do think that pre-processing is extremely important.
Okay, sir.
Thanks, Varu.
More questions, comments? Sakharam. Dinesh. Okay, there are questions, Aditya.
Yes. What limits the number of input tokens in BERT? That's a good question. So I think they apply some sort of occurrence-based threshold. Occurrence-based threshold, as in they consider words which occur more than a certain number of times. And there's also a trade-off between computational requirement and so on, right? So you how when we are training a BERT in the industry, for example, we may actually cut off tokens which occur less than a certain number of times just because we want to get the model running very fast and up very fast, or we want to retrain the model fast or meet a certain deadline. So I think in that sense, the number of input tokens in BERT would be limited by the computational processing power, the expected time, etc. And it is also manifested in the form of thresholding. I think BioBERT, on which corpus BioBERT model is trained, it is, I think, trained on biomedical documents. But you can, so I'm not sure if it is transcripts or if it is biomedical literature. It could be one of the two, but you can confirm. Dinesh asks, can BERT be used to generate text answer to questions apart from finding answer spans? Do you need a decoder in that case? Yes, I think you would need a decoder in that case, because BERT essentially learns to, I'm not sure how you'll train. Yeah, I think you would need a decoder, and you can actually use a transformer based model for generating answers from BERT. Well, yeah, so you need an encoder and a decoder. Sandeep has asked, Sir C.V. Raman got his second dash in 1930. If BERT predicts Nobel Prize, then it is factually incorrect, right? So this is hallucination. How does BERT solve this? Yeah, this is a very difficult question. This is a very difficult question, because I think this particular example has two things. Validity of meaning and truth value, right? So I mean, and therefore I'm not sure how BERT handles truth value explicitly, because in itself it is just applying multi-headed attention, as a result of which it is going to rely on the data to not predict Nobel Prize incorrectly, even if it matches the context, for example. And therefore I do not know how BERT specifically focuses on truth value of sentences as opposed to the meaning or the grammaticality. With such powerful models at hand, how important is feature engineering for NLP? Oh, it is very important. I think it is still very important, and it is a lot of mix and match of BERT and other features is very commonly used in industry. So I think, yeah.
Okay, sir.
It's quite powerful. And I've answered Kaveri's question. More questions on? I think is there any specific reason for using multi-headed attention as opposed to single-headed attention? I think the specific reason is, I think the possible reason is to allow multiple spans of words to interact with each other. So it is in some sense permutation. So for example, it's like just trying it out multiple times so that it can attend to different aspects of the data or different features or dimensions of meaning. So I think attending to different dimensions of meaning is a reason, according to my understanding, why multi-headed attention is used for BERT.
So in some sense, it provides a sort of ensembling effect. Is that the case?
Ensembling effect?
Like we have ensemble of different
Oh,
models.
yeah, yes. No, I wasn't sure if you said sampling or ensembling. That's why, yes, I think it offers some sort of an ensembling effect.
Okay.
Is BERT trained to filter out strong language? Not that I know of. I mean, I don't remember reading it in any of the fundamental BERT papers. But if you are interested in how BERT-based models are fine-tuned or adapted to remove biases or remove strong language, etc., I would urge you to look at some of the debiasing papers in NLP conferences. And these days now there's a track on debiasing, removing biases in language model and so on. Is BERT a generative model? Can it be used as a discriminative model? The way I see it, BERT's ability to generate masks, the whole base of the vacuum cleaner, is the generative component. And when you apply these heads on the top to fine-tune BERT for specific tasks like sentiment classification, question answering, it is being used as a discriminative model. That's how I see it. But this is a tricky question.
Okay, any other questions, comments?
So word to oh wow, lots of questions. How are word to embeddings different from BERT embeddings for ambiguous words like bank? Word to embeddings do not take into consideration the context, and therefore the vector for bank would be the same across all the meanings of bank. That is understood to be one of the issues of word representations, which led to the advent of contextual representations, which is BERT embeddings. How important is the intuition behind the design of such architectures? Do we iteratively make the design better by looking at the flaws of a previous iteration? Do we first fix it mathematically, then code it, finish the design in one shot? Yeah, this is a difficult question again. I do feel that, at least as a reader of NLP papers and somebody who implements and uses these architectures at work, I prefer to read the mathematics first and then go on to trying out a bit of the code to build my intuition. So as a person who understands these models and uses them, I go actually the other way. I build my intuition via experience, and that could just be my style of understanding things.
Okay, sir.
Why? Okay, Abhishek asks a question about autoregressive models in GPT-3. Abhishek says, "Wow, these are lots of questions." Okay. Why did we go back to autoregressive language modeling in GPT-2 given the power of masked language models? So I think I imagine, and the reason I wanted to bring up that distinguish between in autoregressive and autoencoding is really this question which Abhishek asks. The NLP field today, in my understanding, is a pendulum which oscillates between autoencoding, autoregressive, which says what does it mean by capturing the meaning of language? Does the meaning of a word depend only on the words before it or around it? And I think this seems to be a trend, in the sense that as newer approaches in NLP seem to try out the other side based on learnings in one side, where the two sides are autoregressive and autoencoding. Masked words prediction may indicate a generative aspect of BERT, but can it also be said for next sentence prediction or part of BERT? Isn't it more discriminative? Yes, it is more discriminative, Paramveer. I agree. Does autoencoder model have significant advantage over autoregressive model, GPT versus BERT? What makes one better? What does autoencoder model have any significant advantage over autoregressive models? Or are they just two paradigms, just two ways of capturing meaning? That is what I'm thinking about. So yeah, I don't have a definitive answer about whether there is a specific advantage of one over the other. However,
I will just add one point. Sorry to interrupt. Maybe
okay.
autoregressive models help us to create better some better results in the generation task because of their autoregressive nature. In autoencoding models, we cannot generate very good languages maybe, but because of autoregressive natures in GPT X models, they are doing very well in generation tasks. That is maybe the one great advantage of this autoregression paradigm.
Yeah, that's a very interesting perspective, because a decoder in a transformer is essentially autoregressive, like you pointed out, Neha.
Yeah.
Nihar, was it right?
So if I may add something here, Aditya. So auto-regression is based on previous k words predicting the k plus 1 word. And masked models are any masked words being predicted from the other contextual words. So it seems to me that shallow parsing is more suitable for autoregressive models because they rely on small windows of context, whereas word sense disambiguation, agreement generation, they would be better serviced by autoencoding.
Yeah. So actually, the reason why I asked this was like, I see that GPT has like so many billions of parameters and all. So does this paradigm in any way affect like for GPT performing better, or is it just the number of parameters? Not sure. Just wanted to know about that. Like, is the paradigm affecting it, or it's just like because it's trained on such a large amount of data and such large amount of parameters? Is that the reason why GPT is doing better, or how is it?
Can I say something?
Yeah.
I don't believe it's just the parameters, because there are variants of GPT, let's say GPT-J, GPT-Neo, they have very small parameters as compared to original GPT, but they do perform well. It depends on the paradigm more than the data or number of parameters.
And I think on 8 December there was a paper from DeepMinds. They call the system retro, and they say that with 25 times less number of parameters, they have equivalent performance of GPT-3. So lots of optimization is possible. So many parameters are not really needed. So if the question is where does the power come from? Does it come from the parameters, or does it come from the data, huge amount of data? I think we can trace it to the data.
Sir, can I add something, sir?
Yeah.
Sir, I have worked with GPT-2 and defined that there is an impact of number of parameters being used. I have used 125 million and 375 million parameters, and so the output for 375 million is much more better than 125, because the number of repetitions also decreases and all those things also decreases. So I would say that parameter do play like some important role in the generation task. So that's all. That observation from my experiments.
I see. Yeah. So I may be wrong then. You have to understand more.
No, maybe Sakharam's question was specifically if the paradigm, the way bot and GPTs are trained, they play a heavy role in terms of different task performance or not, as compared to parameter. So paradigm we cannot ignore, I believe. Paradigm is important. When paradigm is fixed, then the number of parameters is another level of importance for that particular paradigm, or how many number of parameters in different variant of that model. If parameters for that particular paradigm is more, then it will perform better than the lower number of parameters for that particular paradigm. But when we compare paradigms, definitely paradigm has different importance in different tasks. Cannot ignore that.
Two more questions, Aditya, and maybe they will be the last.
Sure. Yeah. So can we use inverse probability of sentence given word at position in computation rather than word n given word n minus 1 to word 1? What difference can it have? I'm trying to understand what probability of sentence given word at position n really means, because it would be something like generating, it would be like generating a text from a prompt. Is that the task that we're talking about there? So
Yes, sir.
so it's like prompt based generation of text. So I see that if you use that probability, then we would be operating in the prompt-based generation of text scenario. And was your question about, can we use this for language modeling?
Yeah, for the language modeling.
Mm-hmm. So essentially, you're saying that there's a self-supervised corpus or an unsupervised corpus, and you have a self-supervised model, which learns to generate a sentence based on a random word in the sentence. Right? Sorry.
Yeah, what I wanted to ask is, so instead of having the context of the n minus words a priori, can we use the like entire sentence and then we need to predict the mask sentence using one particular word, right? So can we use this computation rather than the context computation?
Yeah, I think it's an interesting idea. Although I'm not familiar with work which directly does it the way you described. Yeah. I'll move to the next one, Sandeep, if that's okay. Is there any prevalent adversarial generation technique apart from autoencoder or regressor for language? I've heard of I've heard of and used variational autoencoders. I could point you to papers, Swaroop, later, which use adversarial networks for generation.
Okay, sir.
But I'm not sure if they are not using autoencoder or autoregressor at all.
Oh, okay, I'll have a look at them.
Okay.
Thank you for all these questions, and thank you for the opportunity, sir. And these questions make me relive my Seafield days, and it makes me realize the questions made me realize that Seafield is as strong as always.
Thank you. And also, Naveen has pasted the link for this new paper on retro.
Thank you.
Thank you, Naveen. So take a look at this. And yeah, thank you, Aditya. Thanks for your time, bringing in both concepts and hands-on practical tips also. And you are Seafield senior, so students might write to you for guidance and so on.
Sure, absolutely. Thank you. Thanks.
Okay. Thank you, everybody, and we'll meet for the information extraction of work update.